Far beyond the familiar stars of our own galaxy, beyond the quiet spiral arms of the Milky Way, there exists a cosmic giant so enormous that it reshapes the space around it. Its name is Messier 87. For centuries, it appeared as nothing more than a faint, blurry patch of light in the constellation Virgo, a smudge in the sky, a distant galaxy among thousands. But that smudge hides something extraordinary. Messier 87 is not just another galaxy. It is a colossal, elliptical titan containing trillions of stars. At its center lies one of the most massive black holes ever observed. A black hole so immense that its shadow was the first ever photographed by humanity. And yet, even after capturing the image of its event horizon, even after measuring its jet of plasma stretching thousands of light years into space, astronomers were still asking a deeper question. How big is Messier 87 really? Because measuring something so vast is not simple. Galaxies do not have sharp edges. Their light fades gradually into darkness. Their halos stretch invisibly into intergalactic space. Their gravity reaches farther than their glow. To understand the true size of Messier 87, scientists had to rethink what size even means on a cosmic scale. Is it the visible stars, the dark matter halo, the reach of its gravity, the length of its relativistic jet, or the influence it exerts over the surrounding Virgo cluster? What we've discovered is astonishing. Messier 87 is not just large. It is vast beyond ordinary comprehension. A structure so enormous that it dominates an entire region of the universe. Tonight, we will travel 55 million light-years away, to the heart of the Virgo cluster, to the galaxy that changed how we measure cosmic giants. This is the story of how we finally began to understand how big Messier 87 really is. Before we can understand how large Messier 87 truly is, we need to understand what kind of galaxy it is. Because not all galaxies are built the same. When most people imagine a galaxy, they picture something like the Milky Way, a graceful spiral of stars, dust, and glowing gas, rotating in delicate arms around a bright central core. Spirals are structured. They are organized. They have patterns we can recognize. Messier 87 is nothing like that. It does not have spiral arms. It does not have neat lanes of dust tracing elegant curves. It does not even have much cold gas left to form new stars. Instead, Messier 87 is what astronomers call a giant elliptical galaxy. From a distance, it appears smooth and round, like a soft, glowing orb suspended in darkness. But that smoothness is deceptive. Inside that glow are trillions of stars packed together in a vast, three-dimensional swarm. No clear disk, no defined structure, just a colossal gravitational sphere of ancient starlight. Messier 87 is located about 55 million light-years from Earth, in the constellation Virgo. It sits near the center of the Virgo cluster, a massive collection of more than 1,000 galaxies bound together by gravity. And this location matters, because Messier 87 is not just a member of the Virgo cluster, it dominates it. If you were able to travel to the Virgo cluster and observe it from afar, you would notice that many of the surrounding galaxies seem to orbit around a central region. That region is controlled by Messier 87's enormous gravitational pull. In many ways, Messier 87 is the anchor of the cluster. This alone suggests immense size, but the true scale goes far beyond what early astronomers imagined. Messier 87 was first catalogued in 1781 by the French astronomer Charles Messier. At the time, it was simply listed as M87, another fuzzy object that was not a comet. There was no way to know that it was an entire galaxy far beyond our own. It wasn't until the 20th century that astronomers began to realize the true nature of these faint smudges in the sky. Edwin Hubble's work in the 1920s demonstrated that many of these objects were not nebulae within the Milky Way, but entire galaxies, island universes millions of light years away. Messier 87 was one of them. As telescopes improved, astronomers began to study its structure more carefully. They noticed something unusual. Emerging from its center was a narrow beam of light, a jet extending thousands of light years into space. This jet was first observed in the early 20th century, but its nature was not understood for decades. It would later be revealed as one of the most dramatic features in the entire observable universe. But before we reach the black hole and the jet, we need to focus on the galaxy itself. If you measure the visible portion of Messier 87, the region where starlight is bright enough to detect easily, it spans roughly 120,000 light-years across. That is already comparable to the diameter of the Milky Way, but that number is misleading.
Because the visible light does not represent the full extent of the galaxy.
Elliptical galaxies do not have sharp edges. Their stars thin out gradually as you move farther from the center. Faint outer halos extend far beyond what early telescopes could detect. Modern deep imaging has revealed that Messier 87's stellar halo stretches much farther than previously thought, possibly up to 980,000 light-years, when including its extended outer envelope and intra-cluster light. That is nearly 1 million light-years. To put that into perspective, the Milky Way's visible disk is about 100,000 light-years across. Even including its halo, it is far smaller than the enormous gravitational domain of Messier 87. But even this still does not capture the full picture, because a galaxy is not just made of stars. It is embedded within a massive halo of dark matter, invisible but measurable through its gravitational effects. Dark matter does not emit light, but it shapes how galaxies rotate and how clusters remain bound together. When astronomers map the motion of galaxies within the Virgo cluster, they find that Messier 87 sits at the center of an enormous dark matter halo that extends far beyond the visible starlight. This halo may span several million light-years. That means the gravitational influence of Messier 87 reaches far beyond its luminous body. It acts as a massive well in space-time, anchoring a large portion of the cluster. And then there are the stars themselves. Estimates suggest that Messier 87 contains between 1 and 2 trillion stars. The Milky Way, by comparison, contains perhaps 100 to 400 billion stars. That means Messier 87 may hold up to 10 times as many stars as our galaxy. But these stars are different. Most of them are old. Elliptical galaxies like Messier 87 are often described as red and dead. They formed the majority of their stars early in cosmic history, then gradually ran out of the cold gas needed to create new ones. What remains is an aging population of red giants and long-lived, low-mass stars. This suggests that Messier 87 is ancient, a relic of early galaxy formation. So how did it grow so large? The answer lies in mergers. Galaxies grow over time by merging with others. Smaller galaxies fall inward under gravity and are absorbed. Their stars are scattered into the larger galaxy's halo. Over billions of years, this process can build truly enormous systems. Messier 87 likely formed through repeated mergers with smaller galaxies in the dense environment of the Virgo cluster. Each collision added stars, gas, and dark matter. Unlike spiral galaxies, which can be disrupted by violent mergers, elliptical galaxies often result from them. When two large spiral galaxies collide, their orderly disks are destroyed. The stars settle into random orbits, forming a smooth, elliptical shape. Messier 87 is likely the result of many such mergers. It is, in a sense, a galactic graveyard, built from the remnants of countless smaller systems. But its most extraordinary feature lies at its core. At the center of Messier 87 sits a supermassive black hole known as M87 star. Its mass is approximately 6.5 billion times the mass of our Sun. For comparison, the black hole at the center of the Milky Way is about 4 million solar masses. M87 star is more than 1,000 times more massive. This black hole alone is larger than many entire star clusters. And it is not quiet. Matter falling toward the black hole forms a glowing accretion disk. Powerful magnetic fields channel some of that energy into twin jets that blast outward at nearly the speed of light. One of these jets extends at least 5,000 light-years into space, and it is visible even in optical telescopes. This jet is powered by the black hole's rotation and the immense gravitational forces at play near the event horizon. In 2019, the Event Horizon Telescope collaboration released the first ever image of a black hole's shadow, and it was M87 star. The image showed a glowing ring of hot plasma surrounding a dark central region. That shadow marked the boundary beyond which light cannot escape. The fact that we could image something so distant and so extreme speaks to the incredible precision of modern astronomy. But it also revealed something profound. The black hole's size corresponds directly to the mass of the galaxy's central region. There is a correlation between the mass of a supermassive black hole and the mass of its host galaxy's bulge. This suggests that galaxies and black holes grow together. Messier 87's enormous central black hole is not an accident. It is part of what makes the galaxy so massive. So when we ask how big Messier 87 really is, we are asking multiple questions at once. How wide is its visible starlight? How far does its stellar halo extend? How large is its dark matter halo? How strong is its gravitational influence? How long is its relativistic jet? Each of these measurements gives a different answer, and each answer reveals a different aspect of its immensity. In the next part, we will look deeper into how astronomers measure these enormous distances, and why defining the edge of a galaxy is far more complicated than it first appears. When we ask how big Messier 87 really is, we are immediately confronted with a problem. Galaxies do not come with borders. There is no sharp edge where stars suddenly stop and empty space begins. Instead, the light fades gradually. The density of stars decreases slowly with distance from the center, dissolving into darkness in a way that resists simple measurement. So how do astronomers measure something that does not have a clear boundary? The answer begins with light. For centuries, brightness was the primary tool for measuring size. Early telescopes could only detect the brightest central regions of distant galaxies. Anything fainter simply disappeared into the blackness of space. When Messier 87 was first studied in detail, astronomers could only see its luminous core and inner halo. That visible region was estimated at roughly 120,000 light-years across, already enormous, comparable to the Milky Way. But as telescopes improved, something remarkable happened. The galaxy grew, not because it physically expanded, but because our instruments became more sensitive. Fainter and fainter stars were revealed, extending the apparent size outward. What once seemed like the edge turned out to be only the beginning of a much larger structure. Modern deep-field imaging allows astronomers to detect extremely faint light from the outer halos of galaxies. When Messier 87 is observed with long exposure times and advanced detectors, its stellar halo stretches far beyond the bright central region. These outer stars are sparse and diffuse. They drift in elongated orbits, often remnants of smaller galaxies that were torn apart and absorbed long ago. Their faint glow can extend hundreds of thousands of light-years from the center. Some estimates place the extended stellar envelope of Messier 87 at nearly 980,000 light-years in diameter, nearly 1 million light-years. But even that may not represent the true outer boundary, because beyond the visible stars lies something even more subtle: intra-cluster light. In dense galaxy clusters like Virgo, gravitational interactions are frequent. Galaxies pass near each other. Some collide, others are stretched and distorted by tidal forces. During these interactions, stars can be stripped away entirely from their parent galaxies. These orphaned stars drift freely within the cluster, no longer gravitationally bound to a single galaxy. Yet many of these stars still remain under the gravitational dominance of Messier 87. This faint glow of free-floating stars creates a diffuse halo known as intracluster light. It is incredibly dim, so faint that it requires extremely careful observations to detect. But when mapped, it reveals that Messier 87's gravitational reach extends far beyond its visible core. So what counts as the size of a galaxy? Is it the region where most of its stars reside? Is it the area where its gravity dominates the motion of surrounding objects? Or is it defined by its dark matter halo? To answer this, astronomers turn to another powerful tool: motion. By observing how stars and satellite galaxies move, scientists can infer the distribution of mass, including dark matter. In the Virgo cluster, many smaller galaxies orbit around Messier 87. Their velocities reveal something astonishing. They are moving under the influence of a massive gravitational well centered on M87. When these motions are mapped, the data suggest that Messier 87 sits inside an enormous halo of dark matter that may extend several million light-years across. Dark matter does not shine. It cannot be seen directly, but its gravitational effects are measurable. And in the case of Messier 87, those effects are immense. The galaxy does not simply exist within the Virgo cluster. It shapes the cluster. The combined mass of its stars, gas, and dark matter may exceed several trillion solar masses. And that mass anchors a significant portion of the cluster's gravitational structure. In fact, Messier 87 may contain more mass than the Milky Way and Andromeda combined. But measuring mass is not simple. Astronomers observe the velocities of globular clusters, dense spherical collections of ancient stars that orbit around Messier 87. These clusters move at tremendous speeds, some exceeding 1,000 kilometers per second. Their rapid motion implies the presence of a powerful gravitational force. By modeling these velocities, Scientists estimate the total mass of the galaxy's halo. The results consistently point to a vast reservoir of dark matter surrounding the visible stars. This halo likely extends well beyond the region where stars are concentrated. So if we include dark matter, the true size of Messier 87 may be measured not in hundreds of thousands of light-years, but in millions. And then there is the jet. The relativistic jet launched from the central black hole extends at least 5,000 light-years from the galaxy's core. In radio wavelengths, the structure is even larger, reaching far into intergalactic space. This jet is powered by the black hole's immense rotational energy. Magnetic fields twist and accelerate charged particles outward at nearly the speed of light. The energy carried by this jet influences the surrounding gas within the Virgo cluster. It prevents some regions from cooling and collapsing into new stars. It injects heat into the intracluster medium. In this way, the black hole does not merely sit at the center of Messier 87. It actively shapes the environment around it. When astronomers consider the galaxy's impact on its surroundings, its gravitational influence, its dark matter halo, its relativistic jet, the concept of size becomes more complex. Messier 87 is not just a collection of stars. It is a dynamic system interacting with its cluster on scales of millions of light-years. To better understand this, researchers use simulations. Advanced computer models simulate galaxy formation over billions of years. These models show that giant elliptical galaxies like Messier 87 grow through hierarchical mergers. Smaller galaxies fall inward, are torn apart by tidal forces, and deposit their stars into extended halos. Over time, the galaxy becomes larger and smoother, its structure less defined but more massive. These simulations suggest that the outer halos of giant ellipticals can stretch far beyond what is easily observable. In dense clusters, the boundaries between galaxies blur. The gravitational fields overlap. Stars drift between systems. Messier 87 sits at the center of this cosmic web. Its position makes it difficult to define where it ends and where the cluster begins. And this is perhaps the most important realization. There is no single number that defines how big Messier 87 really is. If we measure only bright starlight, it is about 120,000 light-years across. If we include its faint stellar halo, it may approach 1 million light-years. If we include its dark matter halo, its gravitational reach extends even farther. If we consider its influence on the Virgo cluster, its effective domain spans millions of light-years. Each method gives a different answer, and all of them are correct in their own way. In astronomy, size is not a fixed property. It depends on what you are measuring and how you define the boundary. Messier 87 teaches us that cosmic structures are layered. There is the visible layer of stars. There is the invisible layer of dark matter. There is the energetic layer of jets and radiation. There is the environmental layer of cluster influence. Together, these layers form something far more immense than a simple glowing sphere in space. And yet, even after measuring its halo, mapping its dark matter, and imaging its black hole, one truth remains clear. Messier 87 is not merely large. It is a central pillar of an entire cosmic ecosystem. In the next part, we will explore the role of its supermassive black hole in shaping the galaxy's growth, and how the black hole's mass helps define the scale of the entire system. At the center of Messier 87 lies something that changes everything: A supermassive black hole, so enormous that it bends space itself on a scale almost impossible to imagine. Its official designation is M87 star. Its mass is approximately 6.5 billion times that of our Sun. To understand what that means, consider this. The black hole at the center of our own Milky Way galaxy, Sagittarius A star, has a mass of about 4 million suns. M87's central black hole is more than 1,000 times heavier. That difference is not subtle. It reshapes the entire galaxy. For decades, astronomers suspected that Messier 87 housed a massive black hole. Observations of stars moving at extreme velocities near the galaxy's center suggested a powerful gravitational source. But the true scale was confirmed through careful measurements of stellar motion and gas dynamics. Stars near the core of Messier 87 orbit at tremendous speeds, thousands of kilometers per second. Their motion reveals the presence of a compact, incredibly massive object. That object is M87 star, and its size is staggering. The event horizon, the boundary beyond which nothing can escape, spans about 40 billion kilometers in diameter. That is larger than the entire orbit of Neptune around the Sun. Let that settle for a moment. The black hole at the center of Messier 87 could swallow our entire solar system and still have room to spare. But the mass of M87 star is not just impressive in isolation. It correlates directly with the mass of the galaxy around it. There exists a relationship in astronomy known as the M-sigma relation, a tight correlation between the mass of a galaxy's central black hole and the velocity dispersion of stars in the galaxy's bulge. In simpler terms, the bigger the galaxy, the bigger its black hole. This suggests that galaxies and black holes grow together. They are not separate entities, they co-evolve. In the case of Messier 87, the enormous black hole reflects the galaxy's history of mergers and mass accumulation. Each time a smaller galaxy merged with M87, its central black hole may have eventually merged as well. Over billions of years, these mergers built a monstrous central engine. And that engine does not remain quiet. One of the most extraordinary features of Messier 87 is its relativistic jet. This jet emerges from the region near the black hole and extends at least 5,000 light-years into space. In radio wavelengths, it can be traced even farther. The jet is composed of charged particles, accelerated to nearly the speed of light. Magnetic fields twist and channel these particles outward in a narrow beam. The energy involved is immense. The jet shines across the electromagnetic spectrum, from radio waves to X-rays. It is powered by matter falling toward the black hole. As gas spirals inward, it heats up, forming an accretion disk. Some of this material does not cross the event horizon. Instead, it is redirected outward along magnetic field lines, launched at relativistic speeds. The jet is not merely decorative, it affects the entire galaxy. The energy released by M87 star influences the surrounding gas within the Virgo cluster. Without this feedback, gas in the cluster's core might cool and collapse into new stars at a much higher rate. But the jet injects heat into the environment. It regulates star formation. It prevents runaway cooling. In this way, the black hole acts as a thermostat for the galaxy. It is astonishing to consider that something smaller than our solar system can control processes spanning hundreds of thousands of light-years. Yet this is precisely what happens. The scale difference between the black hole and the galaxy highlights a deeper truth. Size in the universe is not simply about physical dimensions. It is about influence. M87 star occupies a tiny fraction of the galaxy's total volume, but its gravitational pull and energetic output shape the entire system. In 2019, humanity saw something unprecedented. The Event Horizon Telescope collaboration released the first ever image of a black hole's shadow, and it was M87 star. This was not an artistic rendering. It was a real image created by linking radio telescopes across the globe to form a virtual Earth-sized telescope. The image showed a bright ring of plasma surrounding a dark central shadow, the silhouette of the event horizon. This shadow confirmed Einstein's predictions about gravity under extreme conditions. It also provided a direct measurement of the black hole's mass. The diameter of the shadow matched theoretical models for a black hole of 6.5 billion solar masses. The image did more than confirm equations. It transformed abstraction into reality. For decades, black holes were inferred indirectly. Now, one had been seen, and it belonged to Messier 87. The presence of such a massive black hole reinforces the galaxy's enormous scale. Because the mass of the central black hole is proportional to the galaxy's central bulge mass, M87's bulge must also be immense. Estimates suggest that Messier 87 contains between 1 and 2 trillion stars. The Milky Way, by comparison, contains perhaps 200 billion. That means Messier 87 may contain up to 10 times as many stars as our galaxy. But the stars in Messier 87 are different. Most are old. Elliptical galaxies like M87 formed their stars early in cosmic history. Rapid bursts of star formation occurred billions of years ago, fueled by abundant gas during merger events. Eventually, the available gas was consumed or expelled. Today, Messier 87 forms very few new stars. Its population is dominated by ancient, reddish stars. This makes the galaxy appear smooth and diffuse. Without spiral arms or active star-forming regions, it lacks the dramatic structure seen in galaxies like the Milky Way. But that smoothness masks incredible mass. Globular clusters provide further evidence of M87's scale. Messier 87 hosts an astonishing number of globular clusters, perhaps 12,000 or more. For comparison, the Milky Way contains about 150. Globular clusters are dense, spherical collections of old stars that orbit around galaxies. Their numbers correlate with galaxy mass. The abundance of globular clusters around M87 suggests a deep gravitational well and the history of numerous mergers. Each globular cluster is like a fossil from an earlier epoch. Their orbits trace the galaxy's dark matter halo. Their velocities reveal its mass distribution. By studying these clusters, astronomers refine estimates of how far M87's influence extends, and the answer continues to grow. When we consider the visible stars, the extended halo, the dark matter envelope, the relativistic jet, and the gravitational influence on the Virgo cluster, Messier 87 ceases to be just a galaxy. It becomes a central engine of an entire cosmic region. It anchors the Virgo cluster. It regulates gas dynamics. It shapes its surroundings. It exists on multiple scales simultaneously. So, how big is Messier 87 really? It depends on what you mean by big. If you mean the luminous body of stars, it rivals the Milky Way in diameter. If you include its extended halo, it approaches 1 million light-years. If you include its dark matter domain, its reach spans millions of light-years. If you consider its black hole, it dwarfs entire solar systems. And if you measure influence, it dominates a galaxy cluster. Messier 87 is not simply large, it is layered in scale. In the next part, we will explore how galaxy clusters amplify this sense of immensity, and why Messier 87's position at the heart of the Virgo cluster magnifies its true size beyond the boundaries of a single galaxy. To truly understand how big Messier 87 is, we have to stop thinking about it as an isolated galaxy, because it isn't. Messier 87 sits at the center of something much larger, the Virgo cluster. And this changes everything about how we define its scale. The Virgo cluster is not a small gathering of galaxies. It is a massive gravitational structure containing more than 1,000 known galaxies, possibly many more faint ones yet to be catalogued. It spans roughly 15 million light-years across. That number alone is staggering. For comparison, the Milky Way is about 100,000 light-years across. The Virgo cluster is about 150 times wider. And at the heart of this enormous structure sits Messier 87. Not randomly, not coincidentally, but as the gravitational anchor. When astronomers map the motion of galaxies within Virgo, they observe something fascinating. Many of them are not drifting aimlessly. They are moving in patterns consistent with orbiting a central mass. That mass is dominated by Messier 87. This means M87 is not just large in physical size, it is large in gravitational authority. Imagine standing inside the Virgo cluster. Galaxies are scattered around you in all directions. Spirals, ellipticals, irregular shapes. But as you measure their velocities, you realize something subtle. Their motion is influenced by a deep gravitational well. That well belongs to M87 and its enormous dark matter halo. In galaxy clusters, the brightest cluster galaxy, often called ABCG, typically resides near the gravitational center. Messier 87 is the brightest cluster galaxy of Virgo. But brightness is only part of the story. BCGs grow through cannibalism. Over billions of years, smaller galaxies fall inward toward the cluster center. As they approach M87, tidal forces stretch them. Stars are stripped away. Eventually, entire galaxies are absorbed. Messier 87 has likely consumed dozens, perhaps hundreds of smaller galaxies. Their stars are now part of its extended halo. This process does not create dramatic spiral arms or visible scars. Instead, it builds a diffuse, smooth envelope of ancient stars. That envelope extends far beyond the bright central core. In deep images of the Virgo cluster, faint arcs and streams of stars can sometimes be seen, remnants of galaxies torn apart by gravitational interactions. Some of these streams connect directly to Messier 87. They are cosmic fingerprints of past mergers. Each merger added mass. Each added stars. Each increased the size of the halo. And with every absorbed galaxy, the gravitational dominance of M87 grew. But there is something even more important. Galaxy clusters are filled with hot, ionized gas known as the intracluster medium. This gas is not bound to individual galaxies. It permeates the space between them, glowing faintly in X-ray wavelengths. The temperature of this gas can reach tens of millions of degrees. Why so hot? Because of gravitational energy. As galaxies move through the cluster, and as gas falls inward toward the center, it is compressed and heated. Messier 87 sits at the center of this environment. Its black hole plays a crucial role here. The relativistic jet from M87 star injects energy into the intracluster medium. X-ray observations reveal bubbles and cavities in the hot gas surrounding M87, structures created by the black hole's activity. This feedback prevents the gas from cooling too quickly. Without it, the cluster's central gas might collapse into intense star formation. Instead, the black hole regulates the temperature. This means the black hole does not only shape its host galaxy, it influences the entire cluster environment. The scale of influence expands again. Messier 87 is not only large in stellar mass,
it is large in environmental impact. And this impact extends across hundreds of thousands of light years. Now consider dark matter again. Clusters of galaxies contain far more mass than can be accounted for by visible stars and gas alone. Observations of galaxy velocities within Virgo reveal that most of the cluster's mass is dark matter. Messier 87's position at the cluster center places it within the deepest part of that dark matter well. Its own dark matter halo blends into the larger cluster halo. This blending makes it nearly impossible to define a precise boundary between galaxy and cluster. Where does Messier 87 end and Virgo begin? The line is blurred because the dark matter halos overlap, because stars drift between systems, because gravity operates on continuous gradients rather than sharp edges. This is the core of the difficulty when asking how big Messier 87 really is. Its visible light gives one answer. Its dark matter halo gives another. Its gravitational dominance within Virgo gives yet another. And its black hole's energetic influence adds another layer still. All of these definitions are valid. None of them are complete alone. There is another dimension to consider: time. Messier 87 did not begin as a giant elliptical. It likely formed through a series of mergers over billions of years. Early in cosmic history, smaller galaxies collided frequently in dense environments. Each merger randomized stellar orbits, transforming spiral disks into smooth elliptical shapes. Over time, M87 grew larger and more spherical. In the early universe, it may have been more compact. Today, it is extended and diffuse, and in the future, it will grow even larger, because mergers are not finished. The Virgo cluster is dynamic. Galaxies continue to move, collide, and interact. Eventually, many of them may be absorbed by M87. In that sense, Messier 87 is not a static object. It is an evolving structure. Its size is increasing, slowly but inevitably. On cosmic timescales, M87 is still growing, and that growth reinforces its status as the cluster's central giant. So when we ask how big Messier 87 really is, we must expand our perspective beyond diameter. We must include its visible stellar body, its extended halo, its dark matter envelope, its supermassive black hole, its relativistic jet, its gravitational dominance within Virgo, its environmental feedback in the intracluster medium, its future growth through mergers. When all of these layers are combined, Messier 87 becomes something more than a galaxy. It becomes a central node in a cosmic web. It anchors a cluster. It shapes intergalactic gas. It grows by consuming neighbors. It radiates energy through relativistic jets. Its black hole warps space-time. And all of this unfolds across millions of light years. Compared to our Milky Way, which is a spiral drifting within the local group, Messier 87 operates on a different scale. It is not just a galaxy among peers, it is a dominant structure in a massive cluster. The Virgo cluster itself is part of an even larger structure, the Virgo supercluster, which includes our own local group. And within that vast arrangement, Messier 87 occupies a privileged gravitational position. It is one of the most massive galaxies within our cosmic neighborhood. So how big is Messier 87 really? It is large enough to anchor a galaxy cluster, large enough to host one of the most massive black holes ever imaged, large enough to extend its halo nearly 1 million light-years, large enough to influence the temperature of intergalactic gas, and still growing. In the next part, we will examine how astronomers compare M87 to other giant elliptical galaxies, and whether it stands among the largest galaxies in the observable universe. By now, Messier 87 has already stretched our sense of scale. It is not just a galaxy. It is a gravitational anchor. It is a black hole powerhouse. It is a central engine of the Virgo cluster. But there is a question that inevitably follows. Is Messier 87 one of the biggest galaxies in the universe? Or are there galaxies even larger? To answer that, we have to zoom out even further. Because while Messier 87 is enormous, it does not hold the record for sheer size. There exist galaxies known as brightest cluster galaxies that dwarf even M87. Some of these giants span more than 2 million light-years across, when their extended halos are included. One famous example is IC 1101, a supergiant elliptical galaxy located in the Abell 2029 cluster. Estimates suggest that its visible diameter alone may exceed 1.5 million light-years. Compared to that, Messier 87's roughly 1 million light-year extended envelope may seem modest. But raw diameter is not the whole story, because size in astronomy can mean several different things. There is physical diameter, how far the stars extend. There is total mass, including dark matter. There is luminosity, how much light is emitted. There is gravitational influence, how strongly it dominates its surroundings. And there is black hole mass. When measured across all these categories, Messier 87 consistently ranks among the most massive and influential galaxies in the nearby universe. Its stellar mass alone likely exceeds 1 trillion solar masses. Its dark matter halo may push that total several times higher. Its black hole is one of the largest ever directly imaged. And its location at the center of Virgo gives it an outsized gravitational role relative to many other galaxies. In some ways, Messier 87 may not be the widest galaxy ever discovered, but it is one of the most dynamically powerful. And that distinction matters, because galaxies are not just measured by how far their stars stretch. They are measured by what they control. Consider this. Messier 87 governs the motion of galaxies within the Virgo cluster. Its black hole regulates the temperature of the intra-cluster gas. Its Messier history has built an extended halo of ancient stars. Its gravitational potential well is deep enough to retain massive reservoirs of dark matter. These qualities make it a central structure in its region of the cosmos. But to understand how it compares to other giants, we must examine how elliptical galaxies grow. Giant ellipticals, like Messier 87, form primarily through mergers. When spiral galaxies collide, their orderly disks are disrupted. Gas clouds crash together, triggering bursts of star formation. Over time,
the combined system settles into a smooth, spheroidal shape. Each merger adds stars and dark matter. Repeated mergers in dense cluster environments create the largest elliptical galaxies. Messier 87's environment in Virgo made it a merger magnet. Smaller galaxies falling toward the cluster center were gradually stripped apart and absorbed. Over billions of years, this process created its vast halo. But in richer clusters, those containing tens of thousands of galaxies, even more extreme central galaxies can form. In those cases, the brightest cluster galaxy can grow to truly monstrous proportions. So where does Messier 87 rank? It is not the largest known galaxy in the observable universe, but it is among the most massive and well-studied giant ellipticals within relatively close cosmic distance. And that closeness matters. At 55 million light-years away, M87 is close enough for detailed observation. We can measure stellar velocities. We can detect globular clusters. We can image its black hole. Many larger galaxies are far more distant and harder to study in detail. In that sense, Messier 87 is our most accessible example of a cosmic giant. It allows astronomers to test models of galaxy formation under extreme conditions. It serves as a laboratory for understanding how the largest galaxies evolve. There is another important factor to consider: cosmic context. Messier 87 exists in a universe that is expanding. On the largest scales, galaxies are not isolated islands, but nodes in a cosmic web of filaments and voids. Clusters of galaxies form at the intersections of these filaments. The Virgo cluster is one such intersection. Messier 87 sits at its center, and by extension, near the gravitational heart of our local supercluster. The Milky Way and Andromeda are part of a smaller group, the local group, which itself is gravitationally influenced by the Virgo cluster. That means Messier 87 indirectly influences our own galaxy's motion. The local group is slowly moving toward Virgo. The gravitational pull of the cluster contributes to this motion. So in a very real sense, Messier 87 exerts influence beyond its own cluster. It participates in shaping the dynamics of our cosmic neighborhood. This is scale beyond simple measurement. It is scale measured in influence across tens of millions of light-years. But perhaps the most awe-inspiring comparison comes when we consider black hole mass. M87 star is approximately 6.5 billion solar masses. There are larger black holes known, some exceeding 10 billion solar masses, but very few have been directly imaged. The black hole at the center of IC 1101 may be even more massive, but it is too distant for the kind of detailed observation achieved with M87. In terms of confirmed and directly measured supermassive black holes, M87 star remains one of the most significant. And its jet, one of the most famous astrophysical structures ever observed, makes it visually iconic. So is Messier 87 the biggest galaxy. Not the widest, not the most massive overall, but it is among the most gravitationally dominant galaxies in its region. It is one of the most massive central cluster galaxies within our observable neighborhood, and it is the galaxy that gave us the first image of a black hole. There is something important in that. Size is not just a number, it is a role. Messier 87's role in Virgo makes it central. Its black hole makes it powerful. Its merger history makes it ancient and layered.
Its halo makes it extended beyond simple boundaries, and its influence makes it essential to understanding cluster dynamics. When we compare it to the Milky Way, the difference becomes stark. The Milky Way is a spiral galaxy in a small group of galaxies. Messier 87 is a giant elliptical at the center of a massive cluster. The Milky Way's black hole is 4 million solar masses. M87's is 6.5 billion. The Milky Way contains a few hundred globular clusters. M87 contains thousands. The Milky Way's halo extends perhaps a few 100,000 light-years. M87's halo stretches close to 1 million, possibly more when including dark matter. In almost every category, M87 operates on a larger scale. And yet, it is still only one galaxy among billions in the observable universe. There are likely other galaxies larger still, in distant clusters beyond the reach of our most detailed observations. But Messier 87 is unique because it is close enough to study intimately. It is a bridge between local and cosmic scales. It shows us what happens when galaxy growth continues for billions of years in a dense environment. It demonstrates how black holes and galaxies co-evolve. It reveals how dark matter shapes structure. It illustrates how cluster centers function. So how big is Messier 87 really? Big enough to anchor a cluster. Big enough to host one of the most massive black holes ever imaged. Big enough to stretch nearly 1 million light-years in faint stellar light. Big enough to influence intergalactic gas across vast distances. And big enough to redefine what we mean by galactic giant. In the next part, we will explore what Messier 87 teaches us about the limits of measurement itself, and why the deeper we look, the harder it becomes to define cosmic boundaries at all. There comes a point in astronomy where numbers begin to lose their meaning. Hundreds of thousands of light-years, millions of solar masses, billions of times the mass of our Sun. We can say these words, we can write the figures, but do we truly understand them? When we talk about the size of Messier 87, we are not just measuring distance. We are confronting the limits of how humans define boundaries in a universe that has none. Because here is the quiet truth. Galaxies do not end, they fade. The outer regions of Messier 87 do not suddenly stop at a sharp rim. Instead, the density of stars gradually decreases. The halo becomes thinner. The light dims. Eventually, it blends into the darkness of intergalactic space. But that darkness is not empty. There are still stars there. There is still dark matter. There is still gravity. So where do we draw the line? Astronomers often use a concept called the effective radius, the radius within which half of a galaxy's total light is contained. For Messier 87, this effective radius is already tens of thousands of light-years. But that measurement only captures the bright central regions. It ignores the faint outer envelope. To probe deeper, astronomers use extremely sensitive detectors and long exposures. They measure light so faint it is barely distinguishable from the cosmic background. In those observations, Messier 87 appears far larger than early telescopes suggested. But even those deep images do not capture everything, because much of the galaxy's mass is dark matter. Dark matter does not emit light. It does not reflect light. It interacts only gravitationally. Yet its presence defines the galaxy's true extent. By observing the velocities of globular clusters and satellite galaxies orbiting M87,
astronomers infer the shape and size of its dark matter halo. These measurements suggest that the halo extends far beyond the visible stars, possibly several million light-years. And here, the concept of size becomes philosophical. If a galaxy's gravity influences objects millions of light-years away, is that not part of its size? If its dark matter halo extends invisibly into intergalactic space, does that not count? If its black hole injects energy into gas far beyond the stellar body, is that not also an extension of its reach? Messier 87 forces us to reconsider what size means. In everyday life, size is straightforward. A mountain has a peak and a base. A building has walls and edges. But cosmic structures are gradients. They do not have walls. They have transitions. The boundary between Messier 87 and the Virgo cluster is not a line. It is a region where gravitational influence shifts gradually from one dominant source to another. This is why different studies report different sizes for M87. Some define its diameter based on visible light, perhaps 120,000 to 200,000 light-years. Others include the faint halo, approaching 1 million light-years. Still others focus on dark matter, extending several million light-years. None of these measurements are wrong. They are simply based on different definitions. And this reveals something profound about astronomy. Measurement is interpretation. When we say Messier 87 is 1 million light-years across, we are choosing a threshold, a point where we decide the galaxy's light is too faint to count. But if we lowered that threshold, the galaxy would grow again. The deeper we look, the larger it becomes. There is another layer to this complexity: cosmic time. Galaxies are not static objects. They evolve. Messier 87 today is larger than it was billions of years ago. In the early universe, it was likely more compact. As mergers occurred, stars were added to its outer regions, building the halo outward. This process is called inside-out growth. The core formed early. The halo formed gradually over time. That means the size of Messier 87 is not fixed even in principle. It is still changing. Future mergers in the Virgo cluster will likely add more stars to its outskirts. Its halo may grow even larger. Its black hole may merge with others and increase in mass. On cosmic timescales, size is dynamic. Now consider another perspective. Instead of asking how wide Messier 87 is, ask how far its gravitational influence extends. Gravity does not stop at visible edges. The gravitational field of M87 extends indefinitely, weakening with distance, but never fully vanishing. In practice, its dominant influence extends until the gravity of neighboring galaxies becomes stronger. But even that depends on environment. Because Messier 87 sits at the center of Virgo, its gravitational field blends with the cluster's overall field. The cluster itself is embedded in the larger Virgo supercluster. And beyond that, the cosmic web. Every scale connects to the next. So perhaps the question, how big is Messier 87, cannot be answered with a single number. Perhaps it must be answered with layers. Layer 1, the luminous core. Layer 2, the extended stellar halo. Layer 3, the globular cluster system. Layer 4, the dark matter halo. Layer 5, the relativistic jet and energetic influence. Layer 6, the gravitational dominance within Virgo. Each layer adds a dimension to its size. Each layer reveals a deeper scale. And when all layers are considered together, Messier 87 becomes less of an object and more of a system, a gravitational system, an energetic system, a historical system built through mergers, a central node in a cluster, a cosmic giant whose true boundaries are defined not by edges, but by influence. There is something humbling in this realization. We often think of galaxies as distant islands of stars. But Messier 87 is not an island. It is a continent, a massive structure embedded in an even larger environment. And the deeper we study it, the more our definitions dissolve. Perhaps this is the final lesson of Messier 87's size. Not that it is merely large, but that largeness in the universe is not absolute. It is contextual. It depends on what you measure. It depends on what you include. It depends on how deeply you look. And the deeper we look, the larger the cosmos becomes. In the next part, we will explore what Messier 87's immense scale tells us about the future of galaxies, and how structures like this may evolve over trillions of years in an expanding universe. When we imagine the future of Messier 87, we have to think on timescales that stretch far beyond human history. Not thousands of years, not millions, but billions, and eventually trillions. Because galaxies evolve slowly, their changes are measured not in lifetimes, but in cosmic epochs. Messier 87 today is already ancient. Most of its stars formed more than 10 billion years ago, when the universe was young and rich in gas. Back then, galaxies collided frequently. Star formation was intense. Black holes grew rapidly. But that era has passed. The universe has expanded. Gas supplies have thinned. Mergers still occur, but less often. And so, Messier 87 has entered a quieter phase of its life. It is now dominated by old stars. Red, cool, long-lived stars that burn steadily for billions of years. Massive blue stars are rare here. Their lifetimes are too short, and the galaxy no longer forms many new ones. This gives Messier 87 a soft, golden glow in optical light. It is a mature galaxy, but maturity does not mean inactivity. Inside its core, the supermassive black hole continues to accrete matter. Its relativistic jet still carves cavities in the surrounding intracluster gas. Its gravitational field still governs the motion of satellite galaxies. And slowly, very slowly, Messier 87 continues to grow. In the Virgo cluster, smaller galaxies orbit inward over time. Gravitational interactions rob them of energy. Their orbits decay. Eventually, they spiral toward the center. When they pass close to M87, tidal forces stretch them into elongated streams of stars. These streams wrap around the galaxy like faint ribbons. Over time, those stars disperse and blend into the outer halo. This process is called galactic cannibalism, and it is ongoing. Given enough time, Messier 87 may absorb many more galaxies within Virgo. Billions of years from now, it could become even larger, perhaps rivaling the most extreme giant ellipticals known. But the long-term future of Messier 87 is tied to something even larger: cosmic expansion. The universe is not static. Since the Big Bang, space itself has been stretching. And that expansion is accelerating, driven by a mysterious force we call dark energy. On local scales, within galaxies and clusters, gravity holds structures together. Messier 87 will not be torn apart by expansion, but on very large scales, galaxy clusters are moving away from one another. In the distant future, billions upon billions of years from now, the Virgo cluster may become gravitationally isolated. Other clusters will drift beyond the cosmic horizon. Their light will redshift into invisibility. Messier 87 and its cluster companions will remain bound together, but the larger universe will fade from view. Imagine standing in that far future. The night sky would be darker than today. Distant galaxies beyond Virgo would no longer be visible. Only the local cluster would remain. Messier 87 would still shine at the center.
Its black hole would still dominate. Its halo would still stretch across nearly 1 million light-years. But beyond that, space would appear empty. Over trillions of years, star formation across the universe will gradually cease. Gas supplies will be exhausted. New stars will no longer form. Galaxies will age. Stars will burn out. White dwarfs, neutron stars, and black holes will dominate. Messier 87 will become a graveyard of stellar remnants, glowing faintly with ancient light. But its central black hole may continue to grow. When galaxies merge, their black holes eventually spiral inward and combine. Gravitational waves ripple outward during these mergers, carrying energy away. Messier 87's black hole could merge with others over cosmic time, increasing its mass even further. It may one day exceed 10 billion solar masses, perhaps more. Eventually, in the unimaginably distant future, most matter in Messier 87 may fall into its central black hole. Stars will wander close and be disrupted. Stellar remnants may slowly drift inward. The galaxy's luminous structure may thin, but the black hole will persist. On timescales of 10 to the power of 100 years, far beyond any current star's lifetime, even black holes will begin to evaporate through Hawking radiation. That process is extraordinarily slow. A black hole the mass of M87 star would take far longer than the current age of the universe to evaporate completely. But given enough time, even it would fade. In that final epoch, Messier 87 would no longer be a galaxy in any familiar sense. Its stars would be gone. Its black hole would be shrinking. Only thin radiation would remain. This is the ultimate long-term fate of all galaxies. And yet, for the next tens of billions of years, Messier 87 will remain what it is now. A colossal elliptical giant, a gravitational anchor of Virgo, a laboratory for extreme astrophysics. Its size today reflects billions of years of mergers and growth. Its future size may increase further as it absorbs more neighbors. But eventually, cosmic expansion will isolate it, and over incomprehensible timescales, even its immense mass will dissipate. There is something profound in this. Messier 87 feels permanent. It feels eternal, but it is not. It is a temporary structure in a changing universe, enormous by our standards, brief by cosmic standards. When we ask how big Messier 87 really is, we are asking about a snapshot in time. Today, its halo stretches nearly 1 million light-years. Its dark matter halo extends even farther. Its black hole spans our solar system. Its gravitational influence shapes a cluster. But in the future, that size will evolve.
growth will continue. Then isolation. Then gradual fading. Size in the universe is not fixed. It is part of a story. Messier 87 is a chapter in that story. A moment when gravity gathered matter into one of the most impressive structures in our cosmic neighborhood. And in the next part, we will explore how studying Messier 87 helps astronomers understand the early universe, and why giant ellipticals like this may hold clues to the first billion years after the Big Bang. To understand why Messier 87 matters so deeply, we have to go backward in time, far backward. Not billions of light years in distance, but billions of years into the past. Because when we observe Messier 87 today, we are not seeing it as it is now. We are seeing it as it was 55 million years ago. Its light began traveling toward us long before humans existed in their current form. But that is only the beginning of the time story. Messier 87 itself is ancient. The majority of its stars formed more than 10 billion years ago, during a period astronomers call cosmic noon, when the universe was most active in star formation. Back then, galaxies were smaller, gas-rich, chaotic. The universe was only a few billion years old. Collisions were common, and in the dense environments that would eventually become galaxy clusters, something dramatic was happening. The seeds of giant ellipticals, like Messier 87, were being planted. Early galaxies merged repeatedly, building larger and larger systems. Gas clouds slammed together, triggering intense bursts of star formation. Black holes grew rapidly, fed by infalling material. Over time, spiral structures were destroyed. Ordered rotation was replaced by randomized stellar orbits. The result was an elliptical galaxy, smooth, spheroidal, massive. Messier 87 is a fossil of that era. Its stars are predominantly old and metal-rich, meaning they formed after earlier generations of stars had already enriched the cosmos with heavier elements. By studying the chemical composition of M87's stars, astronomers can reconstruct its formation history, and what they find is remarkable. The central regions appear to have formed quickly and violently, in massive starbursts triggered by mergers. The outer halo, however, appears to have been assembled gradually, through the slow accretion of smaller galaxies. This layered structure is a record of cosmic history. The core tells us about the early, chaotic universe. The halo tells us about billions of years of hierarchical growth. In this sense, Messier 87 is not just large, it is ancient. It is a time capsule. And its immense size today is the accumulated result of countless past interactions. There is another crucial connection to the early universe. Its black hole. Supermassive black holes appear to have formed surprisingly early. Even when the universe was less than a billion years old, quasars, powered by billion solar mass black holes, already existed. How did such massive objects grow so quickly? Messier 87 provides part of the answer. In dense cluster environments, mergers are frequent. When galaxies merge, their central black holes may eventually merge as well. This process builds increasingly massive black holes over time. M87 star is likely the product of multiple such mergers. Its enormous mass reflects billions of years of accumulation. By studying M87's black hole, its mass, its spin, its jet, astronomers refine models of black hole growth in the early universe. Because while M87 itself is relatively nearby, it represents a stage of evolution that likely occurred elsewhere at earlier times.
In distant galaxies, we observe massive ellipticals that look surprisingly similar to Messier 87, but seen when the universe was younger. This suggests that the processes shaping M87 are universal. It is not unique. It is a nearby example of a cosmic pattern. Now consider something even more subtle. When astronomers measure the light from distant galaxies, they see snapshots of the past. Some galaxies in the early universe already appear large and mature, but they are more compact than Messier 87. Over billions of years, those early ellipticals expanded. How? Through minor mergers, the gradual accretion of small satellite galaxies. This process increases size without dramatically increasing central density. Messier 87 appears to have undergone exactly this kind of growth. Its core is dense and compact. Its outer halo is diffuse and extended. This supports the two-phase formation model of giant elliptical galaxies. Phase 1. Rapid early formation of the dense core. Phase 2. Slow, extended halo growth through mergers. Messier 87 is a textbook example of this model, and because it is close enough for detailed observation, it allows astronomers to test these theories with precision. There is also the matter of globular clusters. Messier 87 hosts thousands of them, far more than the Milky Way. Globular clusters are ancient. Many formed shortly after the first stars in the universe. By analyzing their ages and chemical compositions, astronomers gain insight into when and how M87 assembled its mass. Some globular clusters likely originated in smaller galaxies that were later absorbed. Their presence in M87's halo is evidence of its cannibalistic past. In a sense, each globular cluster is a survivor of an earlier galaxy. Together, they map out the galaxy's merger history. This makes Messier 87 not just a giant, but an archive. Its structure records billions of years of cosmic evolution, and because it sits at the center of the Virgo cluster, it also provides insight into how clusters themselves form. Clusters are among the largest gravitationally bound structures in the universe. They grow by accreting galaxies and smaller groups along filaments of the cosmic web. Messier 87 sits at a junction of those filaments. Its size reflects the cumulative flow of matter along those cosmic highways. When we measure the mass of M87's dark matter halo, we are measuring the result of billions of years of structure formation. And this connects to the deepest questions in cosmology. Dark matter dominates the mass budget of galaxies and clusters. Without it, structures like Messier 87 could not form. By studying how its stars and globular clusters move, astronomers infer the distribution of dark matter. Those measurements test models of cosmic structure formation derived from the Big Bang. In this way, Messier 87 links small-scale astrophysics with large-scale cosmology. Its size is not just impressive, it is meaningful. It reflects the way the universe builds structure over time. From tiny fluctuations in the early universe, to collapsing clouds of gas, to merging galaxies, to giant ellipticals dominating clusters, Messier 87 stands as one of the clearest nearby examples of that journey. And yet, even after all this, we return to the same question. How big is it really? The deeper we look into its history, the more we realize that its size is not accidental. It is the outcome of billions of years of cosmic evolution. Its halo, its black hole, its dark matter, all are products of the same fundamental forces that shaped the universe itself. Messier 87 is not just large,
it is the universe's growth made visible. And in the next part, we will explore how modern instruments, from space telescopes to gravitational wave detectors, continue to refine our understanding of this colossal galaxy and its place in cosmic history. If Messier 87 represents the accumulated history of the universe, then modern astronomy represents our attempt to decode that history. And in recent years, our tools have become powerful enough to change not just what we know about M87, but how we measure it. For centuries, galaxies were little more than faint smudges in telescopes. Even in the early 20th century, astronomers debated whether objects like Messier 87 were part of the Milky Way or entirely separate island universes. Today, we can measure the motion of stars within M87. We can map its dark matter halo. We can image the shadow of its black hole. This leap did not happen overnight. It happened through technological revolutions. One of the most important of these was the development of space-based observatories. The Hubble Space Telescope provided incredibly sharp images of Messier 87's core. It revealed the bright jet emerging from its center, a thin, luminous beam extending thousands of light-years into space. Hubble also allowed astronomers to measure the motion of stars near the galactic center with extraordinary precision. By analyzing the Doppler shifts of these stars, the way their light stretches or compresses as they move, scientists calculated the mass of the central black hole long before it was directly imaged. But optical telescopes are only part of the story. Messier 87 shines across the electromagnetic spectrum. In X-rays, the hot intracluster gas surrounding the galaxy glows intensely. Observatories like Chandra have mapped this gas in detail, revealing bubbles carved out by the black hole's jet. These bubbles are enormous, tens of thousands of light-years across. They are proof that the black hole's influence extends far beyond its event horizon. Radio telescopes add another layer of understanding. In radio wavelengths, the jet becomes even more dramatic. The structure stretches outward in complex filaments, tracing the path of relativistic particles spiraling along magnetic fields. And then came the Event Horizon Telescope. This was not a single instrument, but a network of radio telescopes spread across the Earth, effectively forming a planet-sized telescope. By synchronizing observations from sites in Chile, Hawaii, Spain, Antarctica, and other locations, astronomers achieved an angular resolution capable of imaging the event horizon of M87 star. The result was historic. For the first time, humanity saw the shadow of a black hole. The glowing ring around the dark center matched predictions from general relativity with astonishing accuracy. This image did more than confirm Einstein's theory. It provided a precise measurement of the black hole's mass, and that mass anchors our understanding of the galaxy's overall scale, because black hole mass correlates with galaxy mass. If M87 star is 6.5 billion solar masses, then the galaxy surrounding it must be correspondingly enormous. The image also confirmed something subtle. The size of the shadow directly relates to the black hole's gravitational radius. That radius is determined by mass. In other words, the image itself is a measurement of size, not of the galaxy, but of the most extreme object within it. Beyond electromagnetic observations, there is another frontier: gravitational waves. When black holes merge, they release ripples in space-time. Although M87's black hole has not been directly observed merging with another, its mass suggests that past mergers likely occurred.
Future gravitational wave observatories may one day detect signals from supermassive black hole mergers in galaxies like M87.
These detections
Would provide independent measurements of mass and growth history. Another powerful tool is spectroscopy. By breaking the galaxy's light into its component wavelengths, astronomers determine the ages and chemical compositions of its stars. These data reveal when stars formed and how rapidly the galaxy assembled its mass. Deep spectroscopy of M87's halo shows gradients, subtle changes in chemical composition with distance from the center. These gradients support the idea of inside-out growth. The core formed early and rapidly. The outskirts were added gradually through mergers. This layered structure again reinforces the idea that size is historical. The galaxy's current extent reflects billions of years of accretion. Modern computer simulations also play a critical role. Using supercomputers, astronomers model the evolution of galaxy clusters over cosmic time. When they input initial conditions consistent with the early universe and allow gravity to operate over billions of years, they often produce central cluster galaxies that resemble Messier 87. These simulations show dark matter halos growing through mergers. They show gas cooling and forming stars. They show black holes regulating cluster cores through feedback. When simulation outputs match observations of M87, confidence in our cosmological models increases. In this way, Messier 87 is not just an object of study. It is a test case. It tests our understanding of gravity. It tests our understanding of dark matter. It tests our understanding of black hole physics. It tests our models of galaxy formation. And every new instrument refines those tests. The James Webb Space Telescope, though optimized for infrared observation, may contribute additional insights into the stellar populations of M87's halo. Future extremely large telescopes on Earth will measure stellar motions with even greater precision. Next-generation radio arrays will map the jet in finer detail. Each technological advance sharpens our measurement of size. But even with these tools, uncertainty remains. The outermost regions of M87's halo are incredibly faint. Distinguishing between stars bound to M87 and stars drifting freely in the Virgo cluster remains challenging. Separating the galaxy's dark matter halo from the cluster's larger halo is equally complex. This is why size estimates continue to evolve. As instruments improve, the galaxy may grow again, not physically, but observationally. This pattern has repeated throughout astronomical history. Each time telescopes become more sensitive, galaxies appear larger. Their halos extend farther. Their influence deepens. Messier 87 has grown in our measurements over the decades, and it may grow again. This is not an error. It is the nature of scientific progress. We refine definitions, we lower detection thresholds, we expand boundaries. And in doing so, we reshape our understanding of cosmic scale. Messier 87 teaches us something profound. The universe is larger than our first measurements suggest, and it remains larger than our current measurements suggest. Because every improvement in technology reveals more faint stars, more dark matter, more subtle structure, more layered history. So when we ask how big Messier 87 really is, the honest answer may be this: as big as our instruments can reveal, and probably larger. In the next part, we will explore the philosophical implications of this and what Messier 87 tells us about humanity's place within a universe of structures so vast they defy complete measurement. There is a moment when thinking about Messier 87 where the numbers stop feeling like science and begin to feel like something else. Not fear,
Not insignificance, but perspective. Because once you accept that Messier 87 may stretch nearly 1,000,000 light-years across in faint starlight, that its dark matter halo extends even farther, that its gravitational dominance shapes an entire cluster of galaxies, you begin to understand how small our usual reference points truly are. The Milky Way feels enormous to us. It contains hundreds of billions of stars. It spans about 100,000 light-years. It hosts nebulae, black holes, star clusters, and entire planetary systems. But compared to Messier 87, our galaxy is modest. And compared to the Virgo cluster, it is minor. And compared to the cosmic web, it is microscopic. This scaling upward forces a quiet realization. The universe builds structures in layers, and we live inside only one of the smaller ones. Messier 87 sits at the center of one of the largest gravitationally bound systems in our cosmic neighborhood. It is not just a galaxy. It is a node in a web of nodes. On the largest scales, matter in the universe forms filaments, vast strands of galaxies and dark matter stretching hundreds of millions of light-years. These filaments intersect at dense junctions, and at those junctions, galaxy clusters form. The Virgo cluster is one such intersection. Messier 87 sits at its core. This means M87 is positioned at a crossroads of cosmic structure. Its immense size is not random. It reflects its location at a gravitational focal point, where matter has accumulated for billions of years. In this sense, its size is not only physical, it is topological. It is large because it is central. And that centrality has philosophical weight. We often imagine the universe as a scattered collection of galaxies drifting apart. But the reality is more structured. Clusters form. Superclusters form. Filaments connect them. Voids separate them. Messier 87 is part of this architecture. Its size is a consequence of gravity working over unimaginable spans of time. And gravity is patient. Over billions of years, gravity gathers. It pulls, it merges, it deepens wells. Messier 87 is what happens when gravity is allowed to operate in a dense region for nearly the entire age of the universe. Now consider something even more striking. If we could somehow shrink the Virgo cluster to the size of a city, Messier 87 would be its downtown core, the place where density peaks. And the Milky Way? We would be in the suburbs. In fact, the local group of galaxies, including the Milky Way and Andromeda, is slowly moving toward Virgo. Not fast enough to collide anytime soon, but fast enough that its gravitational pull influences our motion through space. That means Messier 87 indirectly affects the trajectory of our galaxy. Not in a dramatic way, not in a way that alters daily life, but in a cosmic way. Our galaxy's motion is part of a larger gravitational dance in which M87 plays a leading role. And yet, even Messier 87 is not permanent. In the far future, cosmic expansion will accelerate. Distant clusters will move beyond our observable horizon. Light from galaxies outside our local supercluster will redshift into invisibility. Eventually, Virgo and the local group may form a gravitationally bound region isolated from the rest of the universe. In that distant era, observers inside that region would see only a handful of galaxies,
including Messier 87, against a dark, empty sky. The broader universe would be unreachable, its light forever stretched beyond detection. Messier 87 would still be large, still central, still dominant, but it would exist in isolation.
And over even longer timescales, stars would burn out, galaxies would fade. Black holes would slowly evaporate through Hawking radiation. Messier 87's immense mass would not protect it from this fate. Its size would not guarantee permanence. Its dark matter halo would remain, but luminous structure would thin. This realization changes how we think about size. Size does not mean immortality. Size does not mean invulnerability. Even the largest galaxies are temporary configurations of matter and energy. Messier 87 feels vast because we compare it to human scales. But on the scale of eternity, it is transient. There is something strangely comforting in that. It means the universe is dynamic. It evolves. It reshapes itself continuously. Messier 87 is a chapter in that story, not the final one. And perhaps that is why studying it matters so much. Because by measuring its size, by mapping its halo, weighing its black hole, tracing its globular clusters, we are not just cataloging numbers, we are understanding how the universe organizes itself. We are learning how gravity sculpts structure. We are discovering how time layers complexity onto matter. We are seeing the consequences of cosmic evolution written across 1,000,000 light years. And in doing so, we gain perspective. Perspective on our place, perspective on scale, perspective on time. Messier 87 does not diminish us. It contextualizes us. It shows that we live in a universe capable of building structures far beyond everyday imagination. And yet, we can measure them. We can image their black holes. We can calculate their masses. We can map their halos. The same species that once looked at faint smudges in the sky and wondered what they were, has now photographed the event horizon of one of the largest black holes in the nearby universe. That may be the most extraordinary scale shift of all. Not the size of Messier 87, but the size of our understanding. In the final part, we will bring all of these layers together: light, dark matter, black holes, clusters, cosmic time, and answer one last time the question that began this journey. How big is Messier 87 really? When we step back from all the measurements, all the simulations, all the images and numbers, we return to a simple question. What does it actually mean for something to be big in the universe? Messier 87 forces that question into the open, because every time we try to define its size with a single number, that number feels incomplete. If we say 120,000 light years, we are only describing its brightest central region. If we say nearly 1,000,000 light years, we are including its extended stellar halo. If we say several million light years, we are counting its dark matter envelope. If we speak of the Virgo cluster, we are including its gravitational domain. Each answer is correct, and yet none fully capture the whole. Messier 87 is not large in one way. It is large in layers. Layer 1 is visible light. This is what telescopes first revealed: a smooth elliptical glow, brighter at the center, fading outward. Compared to spiral galaxies, it looks calm and featureless, but that calmness hides scale. Even this visible body rivals the Milky Way in diameter
and surpasses it in stellar mass. Layer 2 is the halo. Beyond the bright core lies a diffuse sea of stars, ancient, faint, loosely bound. These stars extend far beyond the main luminous body. They are relics of cannibalized galaxies, scattered into elongated orbits. This halo stretches the galaxy outward to nearly 1,000,000 light-years, dissolving into darkness. Layer 3 is globular clusters. Thousands of them orbit Messier 87, far more than orbit our own galaxy. Their distribution maps the depth of the gravitational well. Their motions reveal hidden mass. They trace the invisible skeleton of dark matter beneath the luminous surface. Layer 4 is dark matter itself, invisible, undetectable by light, yet gravitationally dominant. Dark matter halos surround galaxies like immense cocoons, extending far beyond visible stars. For Messier 87, this halo may span several million light-years. It merges seamlessly with the Virgo cluster's larger halo, making boundaries indistinct. Layer 5 is the black hole. At the center of M87 lies a 6.5 billion solar mass black hole whose event horizon could swallow our solar system. Its relativistic jet stretches thousands of light-years. Its feedback regulates hot cluster gas. Its gravitational pull shapes the inner galaxy. Layer 6 is cluster influence. Messier 87 does not merely exist within Virgo. It anchors it. The motions of surrounding galaxies reveal its dominance. It sits at the gravitational heart of a cluster spanning 15 million light-years. When all these layers are combined, the concept of size transforms. Messier 87 is not just an object. It is a system embedded in a larger system. And that larger system is embedded in an even larger one. There is something almost fractal about it. Stars orbit within the galaxy. Globular clusters orbit the galaxy. Satellite galaxies orbit the cluster center. Clusters connect along cosmic filaments. Each scale builds upon the one below it, and Messier 87 sits at a node in this hierarchy. Now consider comparison again. The Milky Way feels immense when we look at it from within. Its disk stretches 100,000 light-years. Its halo perhaps 300,000. But Messier 87's halo may be 3 times larger, perhaps more. Its stellar mass may be 10 times greater. Its black hole is over 1,000 times heavier than ours. It contains more globular clusters than we have stars visible to the naked eye in our entire sky. And yet, even Messier 87 is not the largest galaxy ever found. There are central cluster galaxies in richer clusters that may exceed it in diameter. But few are as well studied. Few have had their black holes imaged. Few are close enough for detailed mapping of halo structure. Messier 87 is both immense and intimate. It is vast, but observable. It is distant, yet measurable. This makes it uniquely powerful as a scientific object. It bridges scale and understanding. There is also something important in how its size evolved over time. Messier 87 did not form large. It grew through mergers, through accretion, through gravitational attraction acting over billions of years. Its present size is not a static property. It is the accumulated result of history. This means its size encodes memory. The outer halo tells us about minor mergers. The core tells us about early starbursts. The black hole tells us about black hole coalescence. The globular clusters tell us about ancient formation epochs. In a very real sense, measuring its size is reading its biography. And that biography stretches across most of cosmic time. When we look at Messier 87, we are not seeing a frozen giant. We are seeing a structure shaped by gravity since the universe was young. We are seeing billions of years of collisions and accretions layered into a single elliptical glow. We are seeing dark matter gathered into a massive well. We are seeing a black hole grown to colossal proportions. And we are seeing the result of cosmic architecture. Filaments feeding clusters, clusters feeding central giants. Messier 87 is the universe's way of concentrating matter. It is what happens when gravity is allowed to dominate in a dense region for nearly 13 billion years. And yet, despite all of this, the deeper lesson may not be about size at all. It may be about scale relativity. Because size in the universe is contextual. A star is enormous compared to a planet. A galaxy is enormous compared to a star. A cluster is enormous compared to a galaxy. And beyond clusters lie superclusters, filaments, and voids. At each step upward, previous giants become components. Messier 87 feels ultimate only until we zoom out further. This does not diminish it, it situates it. It reminds us that even the largest known galaxies are parts of something larger. And that larger structure is part of something larger still. In the final part, we will bring this journey to its quiet conclusion. Not with a number, but with an understanding. Because the true size of Messier 87 may not be a measurement. It may be a realization. When we first asked how big Messier 87 really is, it sounded like a simple question, a number, a diameter, a measurement in light years. But after traveling through visible light, dark matter, black holes, globular clusters, galaxy clusters, cosmic filaments, and billions of years of evolution, the question no longer feels simple. Because Messier 87 is not just big, it is layered, it is historical, it is relational. If we measure only its bright stellar core, we see a massive elliptical galaxy roughly comparable in visible diameter to the Milky Way, though far heavier. If we include its extended halo of faint stars, the number expands dramatically, approaching nearly 1 million light-years across. If we consider its dark matter halo, its gravitational envelope likely stretches several million light-years into space. If we include its position at the heart of the Virgo cluster, its gravitational dominance shapes a region 15 million light-years wide. And if we measure influence, the energy of its relativistic jet heating cluster gas, the motion of satellite galaxies tracing its mass, the way its gravity subtly contributes to the movement of our own local group, then its scale extends even further conceptually. Messier 87 is not defined by a single edge. It fades into the cluster. Its dark matter merges into larger halos. Its gravity blends with cosmic structure. And perhaps that is the real answer. Messier 87 is as big as the layers we choose to see. In the beginning, early telescopes showed a faint elliptical blur. Its size seemed modest. As instruments improved, it grew. Its halo emerged. Its globular clusters multiplied. Its black hole was weighed,
Its jet was mapped, its dark matter halo inferred, its cluster environment analyzed. And then, in 2019, we saw the shadow of its central black hole. Not an artist's rendering, not a theoretical sketch, but an actual image of space-time bending under extreme gravity. That image did not show the whole galaxy. It showed something far smaller, yet far more profound, because within that dark shadow lay a clue to the galaxy's true scale. A 6.5 billion solar mass black hole does not exist in isolation. It forms through mergers. It correlates with galaxy mass. It reflects cosmic history. The size of M87's black hole confirms the enormity of the galaxy surrounding it. But even that is not the end. It is part of a cluster. The cluster is part of a supercluster. The supercluster is part of a cosmic web. And beyond that web lies the observable limit, beyond which light has not yet reached us. Messier 87 is enormous, but it is not ultimate, and that perspective reframes the question. Perhaps we should not ask how big Messier 87 is. Perhaps we should ask what its size teaches us. It teaches us that the universe builds hierarchically. Small fluctuations in the early universe grew under gravity. Gas collapsed into stars. Stars formed galaxies. Galaxies merged into clusters. Clusters connected into filaments. Messier 87 is one of the most spectacular outcomes of that process in our local cosmic neighborhood. Its size encodes billions of years of gravitational work. But our capacity to understand it may be equally extraordinary. So, how big is Messier 87 really? It is nearly 1 million light-years in faint starlight, several million in dark matter. the gravitational heart of a 15 million light-year cluster, home to one of the most massive black holes ever directly imaged, and part of a cosmic web stretching across billions of light years. But beyond all numbers, it is this: a testament to gravity's patience, a monument to cosmic time, a reminder that scale in the universe is layered and contextual, and proof that even the largest structures are only chapters in a much larger story. When we look at Messier 87, we are not just looking at a galaxy. We are looking at the architecture of the universe itself. And in understanding its size, we begin, just slightly, to understand our place within it.